Now let us see one-dimensional conduction in Cartesian coordinate. So here we have the slab. Here we have the slab. The slab has a thickness of L. Capital L is the thickness of the slab. And this is our positive x direction. So here the value of x will be 0 and here the value of x will be L. So the left surface is maintained at temperature T1. It's a prescribed temperature boundary condition or boundary condition of first kind. And on the right side, the temperature is maintained at T2. And we can see that T1 is greater than T2. Since T1 is greater than T2, the heat transfer takes place in the positive x direction. At the bottom here you can see that we have the resistance equivalent circuit for the conduction process here. Q is the amount of heat flowing through the slab, and the driving force is the temperature difference, that is T1 and T2 are the temperature difference that is causing the heat to flow through the material, and it is offering a resistance of L by Ka, which we have studied in the previous class. Now we will use the general three-dimensional equation which we derived in the previous class, and then with the help of that we will be finding out the temperature distribution as well as heat transfer equation for one-dimensional steady state conduction. This is one-dimensional steady state conduction. So there are a few assumptions. So the first assumption is it's a one-dimensional conduction, which means to say that dou T by dou Y and dou T by dou Z will be equal to 0 in the general three-dimensional equation. So since we are considering only heat conduction in x direction, so dou T by dou Y and dou T by dou Z will be equal to 0. That is our first assumption, which means to say that we are assuming there is no heat transfer in Y as well as Z direction. Only heat transfer occurs in x direction. And then the second assumption is it's a steady state conduction. So for steady state conduction, the temperature will not vary with respect to time. So dou T by dou tau will be equal to 0. There is no variation of temperature with respect to time. If I measure the temperature here at the beginning and after 5 minutes, or somewhere here at the beginning and after 5 minutes, the temperature at this point should remain same. There should be no change in the temperature. That is the meaning of steady state conduction. Although here the temperature is T1 and here it is T2, and here within the slab it will be between T1 and T2, although that is between T1 and T2. So, but if I measure the temperature at this point at any moment of time, or at this point at any moment of time, the temperature should remain constant. Okay, then we are assuming there is no internal heat generation, so Qg will be equal to 0, and we are assuming the material of the slab is homogeneous, which means to say that the density is constant, it's not varying, and we are assuming the material is isotropic, which means Kx will be equal to Ky, which will be equal to Kz, which will be equal to K, and we are assuming that it is same in all the direction, that is at x, y and z direction it is same. And then we are also assuming that the thermal conductivity of K is constant. So the thermal conductivity remains constant, so that can be treated as a constant value in the differential equation. So the general three-dimensional equation is dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus Qg by K will be equal to 1 over alpha into dou T by dou tau. This was the general three-dimensional equation which we derived for Cartesian coordinate system. So now with our assumptions, so this term will be equal to 0 because dou T by dou y itself is 0, and this term will also be equal to 0 because dou T by dou Z is also 0. Then there is no internal heat generation, so this is 0. And we are dealing with steady state, so this term will also be equal to 0. Now we are left with only one term in the equation, that is dou square T by dou X square will be equal to 0. Since we have only one parameter on which the temperature depends, so here you can see that the temperature depends only on X direction. So now we can use the definite differential, that is d square T by dx square will be equal to 0. Now what we have to do is we need to integrate this to get the solution, and to integrate this we have the boundary conditions. So the boundary conditions, we have two boundary conditions, that is one on the left side of the slab and the other one on the right side of the slab, and both the boundary conditions are boundary condition of first kind, that is prescribed temperature boundary condition. First one, at x equals 0, T of x, that is T of 0 will be equal to T1. That is the first boundary condition. And the second one is at x equals 0, T of x, that is, sorry, this is at x equals L. At x equals L, T of x will be T of L, and that will be equal to T2. So these are the two boundary conditions which we are going to use to get the solution. So I'll insert a new page now. I'll keep the diagram. Now I have the differential equation, that is d square T by dx square will be equal to 0. Now I'll integrate this. Integrating the above equation, if I integrate it once, I'll get dt by dx, and that will be equal to some constant of integration. I'll call it as C1. Now I integrate it again. If I integrate dt by dx, then I'll get it as T of x, that will be equal to, if I integrate C1, it is C1 into x plus another constant of integration, that is C2. Since we have not applied the limits here for integration, we have to add the constant at the end. So dt by dx, integration of d square T by dx square equals 0 will give us dt by dx, which is equal to C1. Integration of 0 will be a constant C1. Then integrating this, we will get T of x will be equal to C1x plus C2. I'll call this as equation number 1. Now I'll apply the boundary conditions. Applying the boundary conditions, BC stands for boundary condition. The first boundary condition is at x equals 0, at x equals 0, T of 0 will be equal to T1. So from that, in the equation number 1, I'll substitute that. So at x equals 0, temperature will be T1, that will be equal to C1 into 0 plus C2, which implies C2 will be equal to T1. Now second boundary condition, at x equals L, T of L will be equal to T2. Now I'll substitute that in equation number 1. So temperature is T2 here, that will be equal to C1 into L plus C2. I know that C2 is T1, so I can write T2 will be equal to C1 L plus T2. I need C1, so I can write C1 will be equal to this is T1 C1 will be equal to T2 minus T1 divided by capital L. So this gives us the value for C1 and we have the value for C2 as T1. Now I'll substitute those values in equation 1. So equation 1 was T of x will be equal to C1x plus C2. Now substituting the values of C1 and C2 in equation 1, we get T of x, that is temperature at any point x, will be equal to C1 is T2 minus T1 divided by L into x plus C2 is T1. So this is the temperature distribution equation in Cartesian coordinate for one-dimensional steady state heat conduction. Now, by looking at this equation, we have two observations that can be made. First one is, we can see that the temperature distribution is linear. There is no power for x. So all other terms are constant here. T1 is fixed, that is the temperature on the left face. T2 is fixed, that is temperature of the right face of the slab, and L is the width of the slab, which is also fixed. So the only variable is x and the power of x is 1. So we can see that the temperature distribution is linear within the slab. So for one-dimensional steady-state conduction in Cartesian coordinate, the temperature varies linearly within the slab. And the second observation is the temperature distribution is independent of K. There is no K term here. I have only temperature 1, temperature 2 and L as well as X. So the temperature distribution is independent of K, which means to say that it is independent of material. If the temperature distribution is, if the temperature T1 and T2 are same and the thickness is same, then the distribution will also be same for different materials. So these are the observations which we can draw from the above equation. Now let us find out the heat flux. For heat flux, we know the Fourier's law. Fourier's law states that the heat flux is equal to minus K into dt by dx, where K is the thermal conductivity and dt by dx is the temperature gradient. Or if you want the total heat transfer rate, that is Q will be equal to, capital Q will be equal to heat flux into area. So I can write, which is K into A into dt by dx. Now if you look at the value of C1, so if you look here, C1 is nothing but dt by dx, which is the temperature gradient. So I can use this in the equation. So in the place of dt by dx, so we know that dt by dx is equal to C1, which is equal to T2 minus T1 divided by L. So in the place of dt by dx, I can substitute this and by substituting that, I'll get the equation for heat transfer rate. So Q will be equal to minus K into A into dt by dx. In the place of dt by dx, I'll substitute the value of C1, that is minus K into A into T2 minus T1 divided by L. I have a minus sign here. I can take it inside these two terms. So I'll get the equation as K into A into T1 minus T2 divided by L. So that is the equation for heat transfer rate in Cartesian coordinate one-dimensional heat conduction. And here you can see that dt by dx is C1, which is the temperature gradient, and the temperature gradient is given by T2 minus T1 divided by L, and we know that T1 is greater than T2, which means to say that this term will be a negative term. That's why we have added minus sign here, so that we will get a positive sign or positive value for heat transfer rate when we substitute the values. Okay, so that is the reason why we have negative sign here. So this is the equation for heat transfer rate, and the temperature distribution at any point is given by T2 minus T1 divided by L into X plus T1. So these two equations you have to remember for calculation.